Take anything at all and compress it tightly enough, and it will turn into a black hole. Rock, water, onions, or even one of those small yappy dogs that never seem to stop barking. Cram all that mass into a sufficiently minuscule space, and gravity becomes so overwhelming that nothing can escape, not even light itself. But what exactly does sufficiently minuscule mean? For every object that exists, there is a threshold size. Push something below that threshold, and it stops being an object and becomes a black hole instead. That threshold is known as the Schwarzschild radius. Cross it, and an invisible boundary materializes around the collapsed mass, what we call the event horizon. Light sitting outside that boundary can still get away. Light on the inside is trapped for good. The curious thing is that the Schwarzschild radius can be worked out for literally anything. Take Kylian Mbappé, weighing around 75 kilograms. If you squeezed all his mass down to fit within his Schwarzschild radius, he would become a black hole. That radius would be roughly 10 to the power of negative 25 meters. For comparison, a proton sits at around 10 to the power of negative 15 meters. So you would need to compress a person to a scale 10 billion times smaller than a proton. By everything we understand in physics, that is simply impossible. But the math holds up just fine. Let's try something considerably larger: the entire Mediterranean Sea. Compress all that water down to its Schwarzschild radius, and the resulting black hole would be about 6 nanometers across, roughly the size of a protein molecule. And if we crushed the whole Earth, its Schwarzschild radius works out to about 9 millimeters. Our entire planet, packed down to the size of a marble, a scale we can finally wrap our heads around. That said, tiny black holes do not stick around for long. Over time, black holes bleed away mass through a process called Hawking radiation. The smaller the black hole, the faster it vanishes. A black hole made from a person would evaporate in 35 trillionths of a second. A 40-ton truck would be gone in about 5 milliseconds. A Boeing 747 would disappear in 7 seconds. The Eiffel Tower would hold on for roughly 1 day. The Titanic would last 140 days, and a large aircraft carrier would survive for about 2.7 years. When a black hole finally evaporates completely, all that mass gets unleashed as a colossal burst of energy. How much energy exactly? To set the scale, the Hiroshima bomb released around 15 kilotons of TNT. The most powerful nuclear weapon ever detonated, the Tsar Bomba, released roughly 50 megatons. With that in mind, a Mbappe-sized black hole would release energy equivalent to about 32 Tsar Bombas. A loaded truck would match 17,000 Tsar Bombas. A Boeing 747 would equal 190,000. The Eiffel Tower, 4.3 million. The Titanic would come in at 22 million, and the aircraft carrier hits 43 million Tsar Bombas. An explosion on that scale would leave Earth permanently scarred. Now imagine we compress the whole planet into that marble-sized black hole. What happens to the Moon? Honestly, nothing dramatic. The Moon keeps orbiting, just now around a black hole instead of a planet. As long as the mass stays the same, the Moon doesn't care. It was never attached to the planet itself, only to its gravity. That tells you something about the Moon's loyalty. Appreciate us while you can, Moon. Anyway, let's crush Jupiter next, the most massive planet in the solar system, heavier than all the other planets put together. Compressed into a black hole, Jupiter would fit inside a radius of just 3 meters, about the size of a large van. We are starting to get some volume, but we need to go bigger. Compress the Sun, and the black hole would require a map to make sense of. Its radius would be around 3 kilometers, comparable to the size of a city like Barcelona. The entire mass of our star packed into the footprint of a single urban area. Here is where things get really interesting. A black hole does not have to stay the same size forever. Once it forms, it can keep growing by pulling in gas, dust, entire clouds of matter. It can swallow whole stars, consume entire solar systems, or merge with other smaller black holes, each merger pushing it toward something even more extreme. But here is the thing. No black hole anywhere near the size of a compressed sun has ever been found. What is the smallest one we know of? There is no single definitive answer. Several candidates exist, but the physics points to a minimum of about 3 solar masses to form a black hole at all. And a black hole of that minimum mass would have a radius of around 9 kilometers. Somewhere between the height of Mount Everest at 8.8 kilometers and the tallest peak in the solar system, Olympus Mons on Mars, standing at about 22 kilometers. That is the theoretical floor, surprisingly compact for something we tend to picture as a cosmic monster. You might be wondering, what is the closest black hole to Earth? That title currently belongs to Gaia BH1, sitting 1,560 light-years away. With a mass equal to 9.6 suns and a radius of around 28 kilometers, it is smaller than the Tokyo metropolitan area. The nearest black hole in existence is at an unreachable distance from us, and it is no bigger than a large city. But let's stop playing around with modest objects. Everything above falls into the category of stellar black holes, formed when a massive star dies and its core collapses inward. Time to think much bigger. Intermediate mass black holes are a step up. They tend not to form from a single dying star. Instead, they arise in extremely dense star clusters, where the heaviest objects sink toward the center and set off a chain of violent mergers. A solid example is HLX1. By the most widely accepted estimates, it carries a mass of around 20,000 suns, with a radius of about 59,000 kilometers, practically the size of Jupiter. Some estimates, however, push HLX1 up to 100,000 solar masses. At that scale, its event horizon would stretch to a radius of roughly 300,000 kilometers. Set it next to the Sun, and it would be almost half the diameter of our star. Now for the real leap: supermassive black holes. These are the beasts that sit at the centers of galaxies. At the heart of our own Milky Way lives Sagittarius A star, carrying 4.3 million solar masses. Translated into physical size, we are talking about a radius of about 12.7 million kilometers. And here is the puzzling part. By astronomical standards, that is actually not that large. If you pulled the Sun out and replaced it with Sagittarius A star, Mercury would not even come close to being swallowed. The entity that governs our entire galaxy fits comfortably within the orbit of the solar system's smallest planet. But our central black hole was never going to be the biggest in the universe. A significant step up is M87 star, the subject of the very first photograph ever taken of a black hole, and the dominant force at the center of a massive galaxy. Its mass sits at around 6.5 billion suns, with a radius of approximately 19 billion kilometers. If M87 star replaced the center of our galactic neighborhood, it would not just consume Mercury, it would swallow every planet, including Pluto. The orbit of that dwarf planet sits roughly 6 billion kilometers out. The edge of M87 star reaches 19 billion. That black hole is 3 times larger than our entire classical planetary system. One thing would survive, though: Voyager 1. Launched back in 1977, it is the farthest traveling object humanity has ever sent out, currently about 25 billion kilometers from Earth. If M87 star materialized right now at the center of our system, Voyager 1 would be the sole remaining witness to the fact that we ever existed. So we need something that swallows everything, without exception, the true final boss. Enter Ton 618, a black hole operating in a league that genuinely strains human comprehension. Its estimated mass is 66 billion suns. You could fit M87 star inside it 10 times over. Its radius is approximately 194.7 billion kilometers. To make that tangible, light takes around 11 hours to cross our solar system from one end to the other. To travel from one side of Ton 618 to the other, that same light, moving at 300,000 kilometers per second, would need 2 full weeks. And yet, Ton 618 is probably not the largest black hole in existence. It is simply the largest one we have found. Every time we build better telescopes, every time we peer a little deeper into the dark, the universe finds new ways to remind us how small we really are. Not just bigger than we imagine, bigger than we are even capable of imagining.